Morning, class. Let's see, we're going. Yep. Today's lesson is about power. Okay, so power is a rate of change of energy or a rate of change of work done. So let's see. Let's write power is the rate of work done or the rate of change of energy. See how it does with that. Not bad. Okay, so what I mean by that is that power is equal to work over time. Or the other way to say it is that power equals the change in energy over the time passed. Or sometimes we might call it delta E over delta T. Same idea. So the unit of power is called a watt, okay? The unit of power is a watt. Yeah, that worked out. Not bad. So let's see. 1 watt equals 1 joule per second. No, I knew I was going to mess up. Okay, let's try one more time. 1 watt equals 1 joule per second. Whew. Okay, kind of. Yeah, that's better. So 1 watt is 1 joule per second. So power is watts divided by time. The interesting thing that happens, though, is that don't forget that work, power is work divided by time. Don't forget that work is force times distance. So really, power equals F times distance over time. Didn't like that. Hold on. There, that's better. Work is force times distance over time. Well, distance over time, you know, is velocity. So actually, power is force times velocity also. Force times velocity. And really, so whenever you put a line over the top of something, a horizontal line over the top of something, it means that you're talking about the average. So really, we're talking really, the average power is equal to the average force times the average velocity. If you need to do it that way. Okay, that doesn't look great, but I think you get the idea. Or I could just do, I have an idea. Hold on a minute. There, maybe that shows it better. So let's try an example now. I'm going to do example 13 on page 180. So I'm going to make a new page. And I'm going to go back to the old page. And let's see, do I really need, I don't think I need this stuff. I think I can just go to the new page and solve the problem. Okay, so let's see what the problem is. Example 13 on page 180. Pause it if you need to go get your book. So the average power can be, oh, here we go. A car starting from rest accelerates in the x direction, has a mass of 1.10 times 10 to the third. So I'm going to say, okay, so this is page 180, example 13. Let's see how that does. I better use this other one instead. Page 180, example 13. Okay, so let's see what we have here. We've got mass equal to 1.10 times 10 to the third. So we move that decimal point 3 to the right, and it's going to be mass equals 1100 kilograms. 1.10 times 10 to the third. Okay, 1100 kilograms. Call that a kilogram. Mass equals 1100 kilograms. Okay. All right. So let's see what else we took. Acceleration is 4.6 meters per second squared. Okay. Acceleration is 4.6 meters per second squared. Acceleration is 4.6 meters per second squared. Okay, for 5 seconds. So t is 5.00. T equals 5.00 seconds. Okay, that's all we have. And they're asking us to determine the average power generated by the force that moves this car. So let's see. So basically we're saying power equals question mark. So how are we going to do this? Well, we kind of could do a force and a distance, right? Well, F equals ma. So if you get the force that way, right? F equals ma. So that means that that's going to equal 1100 times 4.6. So let's see, I'll get up my calculator. 1100 times 4.6. 5,060 newtons. 5060 newtons. Okay, so we've got our force. We need our distance. Well, don't forget the old third kinematic equations. Sometimes you do have to go back to them. So remember, x equals v0t plus 1/2 at squared. Close enough. Okay, v0, we're starting out not moving, so we can say that v0t goes away. And we've got 1/2 at squared. Okay, so that's going to be 1/2 times 4.60 times 25. Because that 25 is, oh geez. Let me do this again. Hold on a minute. Okay, so as I was saying, it's 1/2 times 4.60, which is the acceleration, from 25 times 25, because 25 is t squared, t is 5. So let's see, 0.5 times 4.6 times 25 would be 57.5. Okay. 57.5, and this is distance in meters. Okay, we've got F and we've got X. Now remember, okay, so work is force times distance if they're in the same direction, right? So work equals F times, I'll call it x instead of s, same thing. Okay, so that's going to be 5060 times 57.5. And now let's see, take 5060 times 57.5. That's how much work is actually done to accelerate the car. And that is 290,950 joules. Okay, it takes that much energy, that much work. So if we divide that by the amount of time in seconds, divide by 5, that's going to give us the power, because it's the rate of work, the rate of change of energy. That's how much energy had to be put into the car to accelerate it for, at that acceleration, a car of that mass for 5 seconds. So if we want to know the power, we have to say that work was done over the course of 5 seconds. So watts or joules per second, power. So here we have power equals 290,950 divided by 5. So let's see what I get from that. Divided by 5 equals 58190 watts, or 58.2 kilowatts. Let's see what they got as their answer. Yeah, 582 times 10 to the 4th. Yep, the same thing. So that's how much power it takes to accelerate that car for that amount of time at that acceleration. So that's how you do those. Let's see, let me make one for you to try. Let me get a new page. And here's what I'm going to have you solve. All right, so I'm going to ask you, how many watts of power would it take to lift an 800 kilogram elevator, a 'a distance of 10 meters in 5 seconds. Whoops, I was supposed to say 10. Okay, so that's your problem. How many watts of power would it take to lift an 800 kilogram elevator a distance of 10 meters in 5 seconds? So I'm going to pause this. You can pause it, and you can try to come up with a solution. Okay, let's see if I get the same answer. So what do we know? We know that power equals work divided by time. So time is easy, 5 seconds. Work, well, work is force times distance, right? Work equals force times distance. Well, the force to lift an 800 kilogram elevator. Oh, wait, there's a couple of ways we could do this. It's all the same, really. 800 kilogram elevator, okay, so assuming we lift it without acceleration, then we could say that we're lifting it, we're using 8,000 newtons, right? So that's one way to do it. We could say this is equal to 8,000 times 5. Eight times 5 is 40,000, right? 40,000 joules. But if we don't really know about whether or not it was accelerating or not, we could still use our potential energy, right? Because work is also just equal to the change in energy. And if we start out not moving and end up not moving, the only change in energy is the potential energy, which is mgh, right? Because this is going to be the change in kinetic energy plus the change in potential energy. But assuming the elevator is not moving in the beginning and it's not moving in the end, we can say that there is no change in kinetic energy. So we're really talking about change in potential energy. And that's just mgh, right? So that's going to be equal to mgh. Okay, so that's 800 times 10 times, wait, we don't know h yet, do we? That's the issue. Oh yeah, 10. Oh, that was supposed to be a 10 also. Whoops. Let me redo that one first. Equals 800 times 10 times 10. Right, because that's mg is the weight times 10 meters. So that's equal to 8 with 4 zeros. And that is joules. And this one also is going to be 800 times 10 times 10. It's going to be the same, right? Let's see what we got here. Copy, paste. Copy, paste. Either way, we know the work is 80,000 joules. So we just divide it by the time, which is 5 seconds, right? So P equals 80,000 divided by 5. Got my calculator. 80,000 divided by 5 equals 16,000 watts. 16,000 watts, or 16 kilowatts. And that's our solution. It would take 16,000 watt motor to move that elevator the distance of 10 meters in 5 seconds, 16 kilowatts. That's a pretty serious motor powering that elevator. All right, so that's it for today. I'm sure I'll give you some problems to try, but there's not really too much to this, right? Let's go back to the previous page. Okay, so here's what we've got. Power equals work over time, or change in energy over time, or change in energy over change in time, or really average power. Oh, it turns out that that also means that it's force times velocity. So if you can take the average force times the average velocity, that'll give you the power also. So we have two ways to do it. Force times velocity, or work divided by time. Kind of interesting. And that's it for today. Goodbye, and thank you for watching.